now go.
Hello everybody. We're going to take a little bit of time today to kind of talk about uncertainty and significant figures. So this is something we really didn't get a touch on last lab. Mainly the question of just like where do I measure? Where do I stop measuring? How many decimal places do I need to take it out to? Or my measurements do I need to take it out to? So we'll start with kind of what we did in the lab. So if you remember for table A, we did wood, right? So we did wood, and we had masses of like 1 kilogram, 2 kilograms, and it's not 10, it was like 8 kilograms. But our volumes were something along the lines of, I believe we did for 2 for sure. I remember we doing like not 105, but I think we did like something like 5.00 liters. 8 was like, I think 20.0 liters, something like that. And so as you can see, there's kind of like a difference in these decimal place numbers, like how many decimal places we've really been carrying these out to. So at the end of the day, how many decimal places do we need in order to accurately say, yeah, this is our density? Right? We don't really know. So that's where kind of this uncertainty comes in, and how we accurately measure these different measurements that we're trying to do in the lab. So let's say we get this graduated cylinder right here. So as we remember, I kind of talked about this last time, we're measuring at the meniscus for these things. So let's say our meniscus is something like right here, right? So as you see, you've got this graduated cylinder measures by milliliters, so 1 milliliter, 2 milliliter, 3, 4, 5, etc., 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 right? So with the meniscus kind of being in the middle here, it's somewhere between 6 and 7, right? So I'm going to say that this measurement is 6.5 milliliters. Now, so for this one, we know the milliliter spots on these, right? But we don't really know past that, right? So this right here, it's 6.5, but it could be 6.4, it could be 6.6, anywhere kind of in that range, but we're going to estimate that it's 6.5. And so this is what we call uncertainty. So every single kind of measurement that you're going to take in a lab or anything, in order to be the most accurate it can be, you always have your certain figures, which in this case is going to be your 6 right here. I'm pretty confident that this is 6 but not quite 7. And then you're going to have one number that's always an uncertain number. So for here, that's going to be our 0.5 here. We're not really sure where that 0.5, if it's 0.5 or 0.4, but I'm going to guess that it's 0.5, and that's where our uncertainty comes in. And that's how much that this can measure. We'll do another example. So let's say the meniscus goes right on top here, and it hits this 13 line almost perfectly, right? So I'm going to say for sure we got 13 here, but I'm going to put a 0 in there. And now this is just in case, right? So this is our uncertainty number with our 0, because we don't know if it's 0, if it's 0.1, maybe we're seeing something wrong here. But we're gonna, if we're going to measure it out to 6.5 here, there's no reason we shouldn't measure it out to 13.0 here. So that's what we're talking about, this uncertainty. So sometimes, even if you have something that looks accurate, you always want to put that uncertainty digit here. Now, could I say that this is 13.0004 or something like that? Theoretically, but in all actuality, we really can't, because this graduated cylinder is not made to really measure past that point, right? Because we only can really be uncertain about this digit. The rest of this is just like semantics. We can't really, I can't say at all if it's got 3 extra zeros and a 4 extra. It could just be 2 extra zeros and 1 extra zero. There might not even be any extra zeros. So we don't really know. So we can't really measure that out. And this is only accurate enough to that tenth of a milliliter here. So we're going to pull PowerPoint here. And so, let's just click through. There we go. Kind of already talked about this. This must be estimated. It's called uncertain. Measurement always has some degree of certainty, like we kind of mentioned before. I'm uncertain about that tenth of a digit, but that's the only bit that I can be uncertain of. I can't be uncertain to the hundredth of a milliliter or thousandth to a milliliter, only that tenth. So why is there uncertainty? Measurements are performed with instruments. So if you're performing anything with instruments, no instrument can read to an infinite number of decimal places. I can't, no instrument is made for that, right? So which of the balances have the greatest uncertainty measurement? So I can't really measure, like I said, past that 10th digit because that's as far as it's going. For these two, if we're talking about the greatest uncertainty measurement, this one, we've kind of got these mass scales. You're kind of familiar with them if you've ever been to the lab. They have about 3 or 4 decimal places apiece, so we know we can kind of measure that out. Whereas this one, this is kind of those pound measurements you kind of see at like a Publix or grocery store or anything like that. That really only measures by like pounds, not like tenth of a pound. So we can really only be uncertain to the tenth of a pound on this one. So that's all fine and dandy with measurements. But we kind of can reflect these measurements through calculations. Because what if I've got to, let's go back to that lab. I've got to calculate density. I've got these two different measurements. How many decimal places do I need to carry it out in order for me to consider that to be the accurate measurement? And so this is where we get into sig figs, or significant figures. So these are very, very, very important. Thank you, Mr. Hobbs. These are very, very, very important. I will guarantee you using this throughout your entire career. Anytime you have to do anything with math or science or anything, it's very, very important to know these rules because, especially even if you're doing it in a practical sense. Let's say you've become a chef or something like that. And I don't think chefs really use that, so maybe it's a bad example. But regardless, these are really important for you. So we're going to start with some basic rules. Non-zero integers are always significant figures. So anything that is a number that is not zero is going to be significant in your calculation. You never, ever, ever want to just leave it out if you get it. Or leave it out of the significant figure calculations here. So, example, 3,456. How many significant figures? 4. There's 4 non-zero integers. Pretty easy. Now, zeros is when we get into the weird part. Sometimes a zero can be significant as a way to measure accuracy, but sometimes zeros are there just as a placeholder to kind of measure how large a number is. So we've got 3 different types of zeros that we're going to look at. So first, you've got our leading zeros right here. They're going to be marked in red here. Secondly, we have our trapped zeros, which are these green ones right here, where they're trapped between 2 different non-zero integers. And then finally, you've got our trailing zeros right here. And so captivated zeros are in green, trailing zeros are going to be in pink. So, first rule, captive zeros in between integers are always significant figures. So this one's pretty easy to know. If you've got a zero that's hiding between 2 other non-zero numbers, it's going to be significant. So for example, 16.07, how many significant figures are we going to have? We've got 3 integers, 3 non-zero integers, 1 0. But the 0 is in between the 6 and the 7, so we're going to have 4 significant figures. Next up, trailing zeros are significant only if the number contains a decimal point. So, this, which will be a little cringy as an older man talking about Instagram, but let's say you make a really cool post and it gets a ton of likes. And so you go up to your friends and you're like, yo, my new post got 1,000 likes. It was crazy. Unless y'all are that's probably big unless you're somehow Instagram famous and you've got way more than that. Which good for you if you are. But, so that post probably didn't get exactly 1,000 likes, right? But it got kind of roughly around the same like that. So, you're kind of roughly guesstimating about 1,000 likes. So those zeros in that situation, those don't have a decimal place. There's not a 0.5 like or anything. There's not half a like or anything like that. So those zeros aren't significant. Those are used as placeholders just to kind of show how big the number is, right? But in situations where you have a zero that's with a decimal point, those are kind of measured for accuracy. Like for example, like when we did with the meniscus a little bit earlier, when I put down 13.0, I did that as that last digit of uncertainty. Because that digit of uncertainty covers the accuracy of the entire measurement, okay? So let's go down to here. Example 9.300. How many significant figures do we have on this one? Well, if we're following the rules here, we're looking at this rule right here, we know that we've got two integers and two non-zero integers and two zeros. But we know that those zeros are trailing and they're with a decimal point, so we know that's going to be 4 significant figures. Finally, leading zeros are not significant figures ever. If you write out a number, and I think you'll be able to see this one on this side, I'm not going to write 100 with 2 zeros in front of it. That makes 0 sense. Why would I do that? You're just wasting time at that point. So anytime you see a leading zero, 100% not significant. You're probably never really going to see this except on questions about significant figures. Nobody's really going to put zero. I measured 0, 100 grams or something like that. Nobody's really going to put that in a measurement, but it's an important rule to just kind of remember on your back on the backhand there.
But you're also going to see 0.00002.
True. So the other way about this is the when we talk about decimal places here. So that way to write 0, pretty unrealistic. This one, however, fairly realistic. You're going to see this a lot. However, you got to remember that these are trailing or leading zeros here. These leading zeros are never significant. Again, kind of going back to the Instagram thing, these are kind of placeholders to show, rather, instead of how big a number is, it's to show how small a number is. So for this one, you only have 3 significant figures, which is 486 here, but these zeros are here to show how small that number is as a placeholder. Finally, our last rule, exact numbers have an infinite number of significant figures. So this is just any kind of unit conversion mainly. If you're looking at like, for example, 1 inch equals 2.54 centimeters exactly. So you're not going to mess with the significant figures on these because this is just an exact unit measurement. You don't want to really mess with it. And that's pretty much the rule on this one. So we're going to start, and you're going to want to do this on your own time. We've got a couple different significant figures here, or a couple different numbers here, and I want you to find the number of significant figures in each of these numbers. So I would like you to practice that at home, and then we'll kind of, if you want to pause the video and then do it then and then come back to the video, we can kind of go through these very quickly together. I'm not going to cover them too much, but I do want to just at least display it on the board. So, there are your answers for this one. So if you did them correctly at home, good job. If not, definitely try to look over those rules again, see where you went wrong. Probably the trickiest one here that you're probably not as familiar with is here, right here, this 3.29 times 10 to the 3rd seconds here. So this notation is known as scientific notation. We're going to be working on that, and you're going to be doing a little bit of practice at home with that. But just know that in scientific notation, the only part that really matters is here, because this 10 to the 3rd is also kind of a representation of how big the number is, just like those placeholder zeros that we have normally. So if you wrote this out normally, it's a different type of representation of how big the number is, essentially. Again, go with the rest of this. So just, again, do that at home. So now we're going to go into our rules for mathematical operations here. So the first one's pretty simple. We're going to go multiplication and division. Basically, I'm going to say the fancy way to say it, and I'm going to say the realistic way to think about it. So, so the number of sig figs in the result equals the number in the least accurate measurement used in the calculation. So what that essentially means is that the number with the least significant figures, you're going to want to use that many significant figures as your final result here, because that ends up being the least accurate measurement. And obviously, if it's 1 decimal place versus 3 decimal places, or 3 more decimal places, then the one with 3 decimal places is going to be more accurate. But you don't necessarily need that in order to show accuracy within calculations. You just need the one with the least amount of significant figures. So, example, 6.38 times 2.0. So when we take these types of problems, we want to look at how many significant figures there are in each calculation first. So 6.38, that's 3 significant figures, 3 non-zero integers. 2.0 is going to be 2 significant figures because we have 1 non-zero integer and we've got another trailing 0 with a decimal place. And the decimal place means that that 0 is there for accuracy and not for a placeholder. So when we do the calculations, we get 12.76, but when you know that we have 2 significant figures, we round that off to 13. So something to keep in mind while you're doing this, these are just one-step problems, but let's say you have something with multiple steps that you've got to take care of, do not round the significant figures and don't calculate significant figures until the very last part of that problem, because you want to try to keep everything intact up until that last part to try to stay as accurate as possible. And then once you get to that last part, then you want to start rounding towards your significant figures. So it doesn't really apply too much for this problem, but let's say you had an extra step to this problem that you had to divide by 2.5. You would want to keep the 12.76, then divide by the 2.5. You'll still end up getting 2 sig figs, but it'll be a little bit more accurate to what you're actually looking for. Alright, so we got more practice problems here. Again, same method as you used just there. What you're going to want to do is look at the number of significant figures in each of these, find the one with the least number of significant figures.
Go ahead and do 2 or 3.
Do 2 or 3? Alright, so try to do these on your own real quick. I definitely suggest pause the video. I'll go over a few of them, and then the rest I'll just kind of display on the board as why these work the way they are. So we're going to start with this one, 3.24 meters times 7.0 meters. So we know that 3.24 is going to be 3 significant figures, and 7.0 is going to be 2 significant figures because of that trailing 0 that's behind that decimal point there, or the fact that there is just a decimal point here. So the calculator is going to say, when you put it in the calculator, 22.68, but we know that there's only 2 significant figures, so if we round that, we're going to get 23 meters squared. So another thing to keep in mind, remember these units. They're going to be important. If you ever do any kind of calculations, you're going to always want to make sure you have your units in place, because if you forget what your units are, you'll end up getting some wrong numbers here and there, just solely based off of that. So here we've got 23 meters squared, because it is a meter times a meter. Next up here, 100 grams divided by 23.7 centimeters cubed. So for this one, remember trailing zeros are significant and they measure accuracy if there's a decimal point here. So this one is exactly 100.0 grams. Well, maybe not exactly, but these are the ones that are significant here in this number in particular. Over here, so that's going to be 4 significant figures. This one, 23.7, is going to be 3 significant figures, so we know we got to carry this out to 3 significant figures here in order to be the most accurate, or to have the most accurate calculation that we're going to need. So this is kind of an example of that. So the calculator carries this out to 4.219409283. With these numbers like here, is it really realistic for us to assume that it goes out this far? No, not really. Especially in like a measurement, like we can't, if we measured these in real life, there's no way we could accurately say that it goes out this far. So that's kind of the point of sig figs, so that especially when we do calculations with our measurements to kind of find new data and to make new conclusions and verify hypotheses and whatnot, we can only go so far with this. So that's why we use our rules of significant figures. So again, 3 significant figures here, 3 significant figures here with 4.22 grams per centimeters cubed. So this should look somewhat familiar to you. So like I mentioned before, sometimes density can be measured in grams per milliliter. Another way you can measure it is grams per centimeters cubed. Centimeters cubed is also a measurement of volume, which centimeters cubed is directly, like translates directly into milliliters, so it would be kind of the same thing. But that's another way to kind of see density. So if you see that anywhere, you kind of know that that's going to be a density number, essentially, or the density of something. Finally, I'll go over one more. So 0.02 centimeters times 2.371 centimeters. So if we're following our rules again for sig figs, we know that this one is 0.02 centimeters. We know that this is going to be only one significant figure here because leading zeros are never, ever, ever significant. So 0.02, only one significant figure. This one's going to have 4, 2.371, all non-zero integers. So our calculator reads this, 0.04742, and our final answer is 0.05. So remember, when a number is a placeholder, it doesn't necessarily mean you should put in the calculation, because if you just put 5 as your significant digit, that doesn't really tell us what the number is. So you still need those placeholders, but those aren't necessarily there for accuracy. They're there to show how big or small the number is. So remember, again, when you carry it out, 0.05, because we only have one digit, or one significant figure. And then you have the rest of these here. So if you want to look at those, see if you got it right, you can. I'm not going to explain any further on these. We're going to go ahead and move on to our other types of calculations we can do with this, which is, of course, addition and subtraction. So we save, so I know what you're thinking. Why do we do multiplication and division first? Who does that? Don't you remember PEMDAS? Well, I guess that is first in PEMDAS. But generally, you want to kind of start with addition and subtraction. But the reason we don't here is because the addition and subtraction rules are a little bit different, and they're definitely a little bit harder to understand. But as long as you kind of follow the instructions here, you should be fine on these. So for addition and subtraction, the number of decimal places in the result equals the number of decimal places in the least accurate measurement. So basically, for these, when you're dealing with decimals with addition and subtraction, you want to make sure that you're looking at the least number of decimals, and you go off of that to kind of finish your calculation. So, for example, 6.8 plus 11.934. So we know that there's 3 decimal places in 11.934. There's 1 decimal place in 6.8. So our final answer should only go up to 1 decimal place. So our calculator would show 18.734, but we're going to round it up to 18.7, which would be 3 significant figures. If you were just wondering. If it doesn't have a decimal place, you're going to round to a whole number. So essentially you're looking for the leftmost certain digit. So remember, certainty is going to be essentially, for certainty, you're going to look at a non-zero integer, especially when we're looking at whole numbers here. So for example, 5,400 plus 365 is going to be 5,765. However, we're going to round it to 5,800 because the leftmost certain digit is going to be in the hundredth place right here. So you're going to round it to the hundredth place on these. So we've got more sig fig practice here. Excuse me. Here's our calculations here. I'll give you a few seconds if you want to pause the video to go over these, and then I'll quickly run through a few examples here, and then y'all can check the rest of the answers on your own. So we're going to start with this first one here. 3.24 meters plus 7.0 meters. So we know that the decimal places here, we've got 2 decimal places here, 1 decimal place here. Calculator's going to say 10.24, we're going to round it to 10.2 meters. Next up, 100.0 grams minus 23.73 grams. Should look a little bit familiar, all of these should really do, because we're just doing the same thing except with multiplication and division. Or the same numbers rather than the last one, just with multiplication and division. So for this one, again, 1 decimal place here, 2 decimal places here. We're only going to carry this out to 1 decimal place when we actually get our final answer here. So our calculator is going to say 76.27. We're going to round it to 76.3 grams. Finally, our 0.02 centimeters with our 2.371 centimeters. We've got 2 decimal points here, 3 decimal points here. So our calculator will give us 2.391. We're going to round it to 2.39. And then the rest y'all can take care of on your own. Here's the answers for that if you need to check. And if not, we go from there. So we'll kind of discuss and try to practice this a lot more when you come into class next. We're going to try to drill these significant figures as much as we can. Because they are very important, especially calculations, and we're going to be doing these the entire year. So you want to try to familiar yourself with these and be prepared to use proper sig figs so that you can be the most accurate, or the most accurate as you can be when doing these measurements. So make sure to do these practice problems on your own and be ready for class tomorrow, all right?